Hello and welcome back to the Core of Everything. Today we have Professor Paul Olsen on the podcast. Paul is a paleontologist and stratigrapher here at Columbia University, and he focuses on the patterns of evolution and extinction events that respond to and cause climate change over geological time. In today's episode, we're going to talk about the Triassic period. The Triassic, 250 to 200 million years ago, kicked off the age of the dinosaurs. Land was all one big supercontinent known as Pangaea, and it all culminated in a mass extinction event that nearly wiped out all life on Earth. We also want to quickly say that we've got all our episodes on YouTube, including a mini lecture on carbon storage and one I'm going to upload on how the moon formed. And we were notified the other day that we had 2,500 plays on Spotify. So 2,500 people have tuned in, listened, hopefully learned about geology, about earth science. So keep them coming. Thanks so much for the support and enjoy the episode. So let's set the scene. At the end of the Permian, so 250 million years ago, we saw a mass extinction event called the Great Dying. 90% of all life was wiped out, one of the most aggressive, the worst extinction event in Earth's history. We don't really quite know the causes of it. It could be volcanoes, warming temperatures, no one's quite clear. But soon after, it marks the start of the Triassic period, where life rebounded in a big way. And this period saw the rise of the dinosaurs. So let's start with why we think the dinosaurs started to thrive in the Triassic period.
In the Triassic, you had all the continents united in the supercontinent of Pangaea. And what we see in terms of the landscape and the animals and plants on Pangaea is a pretty dramatic segmentation of assemblages along lines of latitude. So the high latitude regions had a different assemblages than the tropical regions. And dinosaurs first appear in the higher latitude regions, so especially in South America. And it's not until, in fact, the end of the Triassic that they become really ecologically dominant on the whole world. So in the Triassic, in the late Triassic, about 232 million years ago, we had the origin of dinosaurs known mostly from Argentina. And these dinosaurs, a lot of them look really similar to each other. Most of them are relatively small, carnivorous forms were dominant, but there were some plant eaters as well. The distant relatives of the giant sauropods arose at that time. So that was at 232 million years. By at least 225 million years, they had spread across the world and were present in the northern higher latitudes as well as in the tropics. But the weird thing is that they were all small, relatively small carnivorous forms in the tropics. There were no herbivore dinosaurs. Instead, what you saw was an enormous diversity of other reptile types. Some of the, especially armored forms, distantly related to crocodilians. There were large carnivorous forms. There were medium-sized armored plant eaters. There were even bipedal crocodile relatives that looked superficially very much like dinosaurs, but had evolved those resemblances completely independently. So then in the higher, and as we go through the late Triassic, in both parts, the higher latitudes in the north and higher latitudes in the south, we get an abundance of medium-sized herbivorous dinosaurs that are often grouped together and called the sauropods, the prosauropods. The prosauropods are mostly bipedal, not exclusively, mostly bipedal, and look like bipedal versions of Brontosaurus, but they're not nearly as big. And they hang around in the higher latitudes in both hemispheres, never colonizing the tropics. And this is a very interesting and problematic feature of that time period. So in terms of climate, what we think was going on was that it was much warmer than today on average. Carbon dioxide was much higher than present. It may have gotten as high as 6,000 parts per million. We're around 425 parts per million right now. So that's an enormous amount more CO2 in the atmosphere. As a consequence, we have no evidence at all of polar ice caps. So the gradient from the tropics to the poles was weaker. Temperature gradient was weaker than it is today. So that was a feature of the Triassic climates. We know from very recent research though, just in the last few years, that although we didn't have ice caps, it was at least freezing, at least in the Paleoarctic in the wintertime, because we find these cobbles and pebbles that were rafted in on lakes with ice, lake ice, seasonal ice. So we know there was freezing. So, and we also know dinosaurs were living there from their footprints. So these dinosaurs were living in seasonally freezing climates. So that's the basic context of the climate. Different than now because of the gradients in temperature were so much weaker. And in fact, an ambitious dinosaur could conceivably have walked from nearly the South Pole to the North Pole in its life.
And in this time period, we're talking, the continents aren't separate like they were today. It was Pangea. They were all one big supercontinent. And so the idea that they couldn't migrate across to the tropics is kind of, they should be able to, right? Because if they're bipedal, they're two legs, they can just walk over to it. Is there any idea of why they didn't move over to that area?
It's clear that the herbivorous dinosaurs must have traversed those tropical regions somehow, because the forms that are present in the higher in the northern higher latitudes are related to the forms in the southern higher latitudes. So they had to cross. Maybe they went along narrow habitable regions that just don't have a good fossil record, but they must have been able to traverse it. But they clearly never became common enough to leave a fossil record. Yet those herbivorous forms are the most common things you find in both hemispheres in the high latitudes. So what we think is probably going on is the extreme high CO2 did what we're predicting high CO2 to do right now. And that is, it doesn't just raise the average temperature of the globe. The most profound effects are actually on the extreme events. So we can see this happening already. This last few months, the world has seen catastrophic storm after catastrophic storm after catastrophic storm in Nigeria, in Europe, in the United States, where the intensity of rainfall, for example, is extremely high compared to what's normal. Conversely, we're also seeing giant wildfires. And so the extremes are getting more extreme as CO2 is increasing. And this is not really surprising because as you warm the planet, you increase the capacity of the atmosphere to hold water vapor, makes dry areas drier, but where it rains, it dumps the rain in larger amounts. This is not a real physical shock, that this is the kind of process we should be seeing. It's also highly erratic spatially. So the same place that might see incredibly intense precipitation in one season might get a drought in another season. So if you now ramp this up to the many times present CO2 that we think was present in the Triassic, you can imagine that the intensity of these events was really high, and the climate in the tropics would have been erratic and unpredictable. And what herbivores need, if you're an active dinosaur with a high metabolic rate, as an herbivore, you need a predictable source of food. And so the suspicion is that the reason these herbivorous dinosaurs never got a foothold in the Triassic, in the tropical regions, was because their food was erratic, the food source was erratic. For some reason, the crocodile relatives were able to hold on in those tropical regions, unlike herbivorous dinosaurs. And we think the reason that is because crocodile relatives never developed the need to regulate their physiologies at really high constant levels. So when the food source went down, their physiology went down. And that way they could get by these great erratic swings of the climate. You see this in the fossil record of charcoal, which have extremely high temperature fires. You see it in the increase in huge flood events on the continents and the sediments. And we think that's why the herbivorous dinosaurs were absent in the tropics. It's not that they couldn't make it at all. It's just that in the face of the competition from things that just did better under the erratic climate, they couldn't get a foothold.
Okay. And by physiology went down, you mean they got smaller? Is that what you mean by their physiology went down?
What I mean by the physiology going down is their activity levels decreased and their use of energy decreased. The kind of thing we see in modern crocodilians, which are carnivorous, of course, but they don't have to eat constantly. They can just stay quiet and calm, and their physiology drops way down, and they can survive for very long periods without eating at all.
Okay. It's surprising though. We're looking at currently timescales of hundreds of years where we see the CO2 spiking. We're talking about here, Triassic was 50 million years. Surely there was a period of low CO2 within that, or at least a global cooling event that meant that the tropics could be habitable for a short period, at least.
We don't have a complete record of detailed record of atmospheric CO2 through the entire Triassic period. The best part we have is in the late Triassic, the last 30 million years or so. There we have a quite detailed record. Earlier than that, like right after the great and Permian mass extinction, there are hints that it started off very high and then dropped really quite low, close to modern levels, and then ramped up for that last 30 million years of the Triassic to really high levels. And then near the end of the Triassic started to drop again. And then if you look at the whole record of CO2 for the rest of the 200 million years after the end of the Triassic, you see CO2 fluctuating, but going down and down and down and down and down, with some ups and downs towards the present. So yes, the CO2 did fluctuate, but for most of the late Triassic, it was way, way above modern levels. So somewhere between, we think, 1,000 and 6,000 parts per million for that almost the whole late Triassic. So that's a dramatic feature of that time. So there was at least apparently one dip in the around 211 million years ago, and then a decline from 208 million years ago to 200 million years. But for most of that span, it was really high.
Okay. Looking at how humans evolved, it's been correlated to the opening of the East African Rift. 1.8 million years ago, the opening of this rift system led to unpredictable climate, fierce changes in the climate, which meant that humans had to adapt, which is believed to speed up their evolution, help them migrate to a place, Europe, for example, or Eurasia. Is there any way to say that the evolution of species of dinosaurs sped up during this Triassic because of the fluctuating or extreme weather events?
It's difficult to say what kind of physical events have an influence in terms of organisms developing special characteristics to deal with them. It's not clear that evolution actually works that way. Evolution can only act on features which are already present and variable in a population. So there may not be a capacity to evolve in a certain direction, as you might imagine would be a good way to go if the environment's changing. That said, because of variations in the Earth's orbit, which are ongoing all the time, there always were climate fluctuations. And when you think about these populations of animals too, you think of a population that's spread out over an area that's kind of like the middle of the population, where you kind of imagine these organisms are in their comfort zone, right? But at the edges, life pushes out. Life pushes out at the edge, and natural selection is going on at those edges of habitability for those particular organisms. And they always exist. There's always an edge. So that edge is a place which is an opportunity for natural selection to be more creative. And it doesn't take a special event to create those circumstances because there's always an edge. Mm-hmm. So, for example, if we take the Triassic, I said it was freezing in the polar latitudes in the wintertime. This means that organisms that are say, can't stand freezing conditions are nonetheless pushing up towards that. And since there are resources there in terms of plants, there's an opportunity for these organisms if they had the right adaptations. So there's natural selection that might push them in that direction. So in my view, you don't need special things to happen for those creative moments to occur in natural selection. Now, there are exceptions to that, of course. If, let's say, there's no freezing in the world, even up mountains, because that's another place organisms are at their boundaries, right? Going up mountainsides. But if it's so warm there's no freezing at all, then there's no opportunity for them to adapt to freezing conditions, right? But in the case of the Triassic, there was. And you could go up mountains, or you could go towards high latitudes, and they'd be there. They'd be as far north as they could live.
See,
right? So that's where there's that evolution could allow them to survive in those latitudes. In fact, that's certainly what I think happened. I think that was the key to dinosaurian success. That they evolved, perhaps, we don't know this for sure because the northern latitudes are very poorly sampled with respect to the key time period at the beginning of the late Triassic. But in Argentina and in Southern Africa, we know that these earliest dinosaurs were living right at the border. We know they were present right at the border of where it would become freezing. Now, we don't know for sure that they lived in those wintertime freezing areas, but my guess is they did, because all dinosaurs and their near relatives like the pterosaurs or the silosaurs would have had insulation in the form of protofeathers. Now, you need that kind of insulation if you have a highly active metabolism and you're very small. Even in tropical regions, you don't see birds and mice and rodents and small carnivores lose their hair in the tropics. So their feathers in the tropics, they still need it. And there's some reason to think that the whole group of reptiles that were the stem of the dinosaurs and relatives, that they did go through a miniaturization event. So the base of the entire group was very, very small, and it looks like they were insulated. So they could have already at the very beginning survived in cold regions. And this became even easier when you get larger than a mouse. And so these animals were thriving in those regions. The herbivores couldn't make it into the tropics, establish themselves in the tropics because of its erratic climate. But small carnivores could, because they have a source of food in all those other forms. In fact, they might even have an edge, right? Because they'd still be able to be active when the other ones are sluggish. Yeah. So that looks pretty clear. It also looks like during the Triassic, late Triassic, dinosaurs, there were much larger forms of dinosaurs in these higher latitudes in both northern and southern hemisphere. and you only had relatively small carnivorous dinosaurs in the tropics. There were large herbivores. By large, I mean elephant-sized herbivores in the higher latitudes in late Triassic. And there looks like there's new evidence that shows there were some very large carnivores as well. Not T-Rex sized, but maybe Allosaurus sized, pretty big animal. So those are existing in the late Triassic, but not making it into the tropics.
Okay. Yes, okay, that makes sense to me. Who'd have thought dinosaurs knew the benefits of cold plunges even then? So, so I think we should move on to the sort of meat and gravy, the meteorite and gravy rather of this. So life was rife, it was thriving, and then people know the extinction event that killed the dinosaurs 66 million years ago. What they might not know is that the dinosaurs survived another mass extinction event 140 million years before then. So things were going very well, and then 3/4 of all living species were wiped out, disappeared. So what do we know about what caused this mass extinction?
At the end of the Triassic, you have a really large diversity on it. In fact, you don't see that kind of diversity on land until quite a bit later. So everything seems to be going well, and then it tanks. And we know there's a physical event that occurs exactly when that extinction is taking place. And that's the eruption of this gigantic volcanic province called the Central Atlantic Magmatic Province. 15 million square miles of Earth is covered by these emplacements and eruptions of molten rock. Now, we don't know that whole area was covered by lava flows for sure. We know a significant part of it was, because we don't know that because the landscape's been eroded enough that a lot of places that had lava flows, that has just been eroded down to a depth you can't see. They've been eliminated completely. But we know that there are lots of places there were deep-seated emplacements of magma that could have fed lava flows. And there are little hints here and there that it did erupt and form lava flows. So over much of South America, maybe a third of the entire area of South America, there are remnants of the Central Atlantic Magmatic Province, which we call the camp for short. The camp, there are various intrusions, igneous intrusions of these magma over about a third of South America. But here and there, where there's a down warping of the crust and sediments are preserved of the late Triassic, you do get lava flows preserved. In fact, every place that there's a basin with appropriate age sediments in it, there are lava flows from the camp. So it may be that much of that 15 million square kilometer area was in fact covered to some extent by lava flows. And we just don't know how much that is. But we do know that the igneous province is that big. That part we know. So this huge igneous event occurred, but in a relatively short amount of time. So we have very, very high precision ages for both the intrusive rocks and the lavas. And all of them are within an interval of less than 1 million years.
Gosh.
So
yeah, I read somewhere, or someone told me that the lava flows would be enough to almost cover the entire surface of the moon.
Well, it's about 3/4 the size area.
That's astonishing.
So it is an astoundingly big event. However, remember, a critical thing is that the environmental effects of these kinds of eruptions are really more dependent on the rate at which things are occurring than the total area or even volume of what's happening. For example, the ocean crust is much bigger than the Central Magmatic Province, and it's entirely igneous. So it's much, much bigger. But of course, that visible crust now took more than 70 million years to form. So more than 100 million years to form. So that's the slow and steady process that has basically no catastrophic effects at all. But when you condense the event into a small amount of time, then all the accessory things that happen with the emplacement and eruption, their intensity increases. It's really the intensity that's the critical factor. So it's the combined area with a very short amount of time involved. And recent work like that of Kent and others have shown, using paleomagnetic data, that that some of these events were extremely condensed down to the scale of human being existence, like 100 years or less. And what we see in this less than a million year record are pulses that are those extremely intense events one after another.
Yes, and the lava flows, when they don't necessarily cover and destroy the habitable lands, but also you're talking about the side effect being the release of gases, harmful gases or aerosols from the volcanic eruptions. And normally it's believed that the release of CO2, enormous amounts of CO2, I believe it's estimated something like at this time there was 20 times the amount of atmospheric CO2 that there is today from these volcanic eruptions. That's believed to a global sort of warming that makes areas uninhabitable. Whereas this paper that came out this week, which I think your first author on, establishes actually there might have been a severe cooling.
So the eruption of the lava flows themselves, of course, where the lava went, it killed off everything that was on the landscape there. However, a healthy dinosaur could walk away from the advancing lava flow. It's not like the flows themselves were particularly catastrophic. However, gases are released during both the intrusion of the magma into sediments. Gases are leaking out at that time, and then they're much more vigorously pumped out during the eruption itself. And we have thought for a long time that carbon dioxide was because we know it did increase during that time period. It increased enormously during the eruption. We have very clear evidence of that from the record that's encased in calcium carbonate nodules that form in soil in equilibrium with the atmosphere, and they record we can take their chemical record apart and see what the CO2 levels were, and then plant leaves also record something about the levels of CO2 because they have little holes in them that they allow CO2 to get in, which they need as their source of carbon. And the fewer there are per unit area, the higher the CO2 would have been. So because they also lose water vapor through this, they want to keep those number of holes as small as possible so they don't desiccate. So those two kinds of proxies of atmospheric carbon dioxide tell us the same story. Carbon dioxide levels in the atmosphere went up enormously during the eruption of the Central Atlantic Magmatic Province and then came back down again. Now, here's the interesting thing. Yeah, they went up super high, double to triple what they were before. However, before, in the late Triassic, they were just as high. So through most of the late Triassic, the carbon dioxides were just as high as they were during the eruption of the Central Atlantic Magmatic Province. The Central Atlantic Magmatic Province looks so profound in terms of the rise of CO2 because it had been dropping before that and drops afterwards. But if it hadn't dropped just before, you wouldn't even know anything happened. So if dinosaurs, and especially non-dinosaurs, were so happy and thriving in those very high CO2 conditions back in the early part of the late Triassic, why would it be such a huge disruption later? So that presents a challenge. Now, if we just look at the organisms that did go extinct on land during the eruption of the camp, during this huge rise in CO2, we see a really interesting pattern. Organisms that have limited distribution to low latitudes, to the tropics, really get hammered. A whole group of plants, conifers that produce pollen with the name of Patina sporites, doesn't really matter, but this type of plant was a really, really common one, making big forests. But in the late Triassic, it's limited to the lower latitudes, but it's a dominant in the lower latitudes. Completely wiped out, completely exterminated during the time of the end Triassic extinction. Never comes back. It's very rare to have plants just wiped out like that. Very unusual. Then if you look at the animals, the dominant animals in the tropics, both carnivores and herbivores, were these crocodilian relatives, often really intensely armored. We call them the pseudotsuchians. Modern crocodilians are actually pseudotsuchians. So, but that was the big group that was dominant in the low latitudes. And all of the large herbivores in the low latitudes were these pseudotsuchians. All pseudotsuchians bigger than about a meter were wiped out globally. So the dinosaurs, not only weren't they affected badly, they expand and take over those tropical regions. Now, what's the difference between those dinosaurs that came in to the tropics and the crocodile relatives that were wiped out? One thing stands out enormously related to their physiology. The dinosaurs had insulation in the form of protofeathers, and the pseudotsuchians, the crocodile relatives, were naked. So does that change look like it was the effect of heat or cold? Everything about those extinctions looked like they preferentially damaged tropical organisms. And tropical organisms that would have no evolutionary experience cold.
So we've got to the point where we see this correlation. We have the dinosaurs essentially with feathers, or we say protofeathers. Is that the right word to use?
Yeah.
They have survived, but the dinosaurs without feathers have been wiped.
No, they're not dinosaurs. The crocodile relatives.
Sorry, the crocodile relatives. Yes, quite.
So we see that the insulated animals with coats on, like the dinosaurs, the relatives, the flying pterosaurs, they survive and actually expand at the mass extinction that wipes out almost all crocodile relatives in the world. And we know from work we've recently done in China, in Northwest China, that in the Paleoarctic, in the late Triassic and early Jurassic, we see some footprints in the late Triassic. We're not quite sure what they are yet. Don't have enough work done, but we know that the ones in the earliest Jurassic, there are dinosaurs, clear, unequivocal dinosaur footprints from the earliest Jurassic that are walking around in the same environments that have seasonal freezing. So we know they're in those seasonal freezing environments. So when volcanic winters occurred from the sulfate aerosols of the Central Atlantic Magmatic Province, the camp, the idea is that these animals already living in places that freeze would be able to get through these volcanic winters, while animals like the crocodile relatives that have no evolutionary experience with cold at all were almost completely wiped out.
Wow. So volcanic winters, meaning that these are just severe cooling events that are associated with volcanic eruptions.
The volcanic winters and that's a term for the extreme cold events produced by the reflectivity of the volcanic sulfates in the atmosphere that are put out by these eruptions. And there is some evidence, it's a little slim right now, but we're working on it, that these that actually show that these volcanic winters did occur.
Oh. And the idea is
And
generally the sulfate, the aerosols would block out sunlight, or how exactly?
yes, the sulfates reflect sunlight very, very well, and therefore cool the earth. And um, we know something about this kind of process. The eruption of the Icelandic rift volcano Laki killed perhaps 6 million people globally. Not direct effects, but indirect starvation.
Hmm.
And of course, also triggered the French Revolution. And that was a tiny eruption. For example, Laki produced about 15 cubic kilometers of lava. Just one lava flow of the Central Atlantic Magmatic Province covered something like 2,400 cubic kilometers of lava. So there are several orders of magnitude bigger signal eruptions. However, when volcanic carbon dioxide gets in the air, or human-produced carbon dioxide gets in the atmosphere, it takes a long time for Earth system processes to remove it. Actually, tens of thousands to hundreds of thousands of years. In contrast, the volcanic aerosols, the sulfate aerosols, they come out in 5 years. So in order to produce a really globally important volcanic winter that had the capacity to drive sensitive organisms to extinction, you had to have a sustained eruption, or many sustained eruptions one after another. If the eruption lasted for 50 years, the volcanic winter would last for 50 years plus 5.
Yeah.
But that's the kind of thing you need. So humans have no experience with an eruption like that. No eruptions on Earth that produce significant sulfur aerosols lasted for a decade, or 2 decades, or 3 decades.
I've heard of the idea that Mount Pinatubo in 1991 released enough sulfate to drop global temperatures by something like 0.5 degrees C for a couple of years.
That's correct.
A bit less extreme than the dinosaurs.
Right. And that's an example of how quickly it leaves the system. But these camp eruptions were way off scale compared to that kind of eruption. If you try to stick that 2,400 cubic kilometers into a year, you get very, very unrealistic rates of lava flow eruption. So they erupted probably over the scale of decades, and then you have another one and another one and another one. Now, we don't really know how cold it got in the tropics, and we don't know whether it was just one really bad volcanic winter or a succession of them that caused the extinction. That remains to be seen how we can test that hypothesis. We don't have that path yet. So we just see that the simplest explanation for the pattern of extinction is that animals and plants that would be sensitive to cold were preferentially wiped out, while animals that were already living in places that were seasonally cold did extremely well. In fact, when you get up to those polar regions and you look for the end Triassic extinction based on the different kinds of plants that disappeared, it looks like almost nothing happened. And that makes perfect sense if they're already living in a place that's freezing. So it's a very consistent pattern pointing to cold as the main culprit. Now, that doesn't mean that CO2 didn't have a role in the overall picture. So one of the interesting things about the CO2 in volcanic winters is you would have had these alternations of extremely warm times and cold times, right? The most of the time it would have been warm like it was earlier in the Triassic, but then it would be punctuated by these very cold events. So that may have had a role. But then a bigger role for CO2 would be in the oceans. The oceans would not be terribly affected compared to the land by these volcanic winters events because the volume of the oceans is so large that they have this thermal inertia, which prevents them from rapidly changing. That's the whole ocean in its temperature, right? But CO2, that the intervals, the longer periods of CO2 driven global warming would warm the oceans, which reduces the capacity of the oceans to have oxygen in them. And then, probably even more important, the CO2 acidifies the ocean. And when you look at the marine life that went extinct, you see that it was preferentially animals that had shells that were made of the type of calcium carbonate, aragonite, that is more soluble than the other common form, which is calcite. So the animals with the aragonitic shells almost exterminated. So ammonites, for example, the coiled cephalopod mollusks that are so characteristic of the Mesozoic, were almost wiped out at the end of the Triassic. Coral reefs were wiped out globally. And the forms that came back afterwards were the modern groups. The more archaic groups were basically eliminated. So you see that's still a very big role for the carbon dioxide from the Central Atlantic and province. And then it would be the change from lower to higher carbon dioxide occurring over a very short period of time. And that makes it very different than what happened earlier in the Triassic when it was on average very high. So if you take, for example, a doubling of CO2, you spread it out over 1 million years, it basically does nothing to acidification. If you take the doubling of CO2 and pack it into 5,000 years, it's catastrophic in terms of acidifying the ocean.
And that's because life can't adapt to it? Is that the idea?
It's a chemical process. It's a chemical process of equilibrization and the change in the different types of way carbon's distributed in the ocean, different kinds of compounds. So
buffering takes
buffering. Yeah, it doesn't have time for that, and so it swings over to acidity. So the result of putting the same amount of CO2 in over 1 million years is actually to make the ocean have more ability to produce calcium carbonate, not less. It's almost sort of counterintuitive that that's the way it works. So the volcanic input of CO2 during the camp would have a completely different effect than the average high carbon dioxide levels, even same amount, same concentration in the earlier part of the late Triassic.
Wow.
The rate is really more important than the magnitude. So the CO2 is still playing a huge role in the mass extinction, just a different kind of role than warming. And with the warming unquestionably did occur, but it's clear that the pattern of organisms on land, the organisms that were affected were not those that would be affected by heat. In fact, what you'd expect, let's make a prediction, if it was heat driving environmental change, organismal change on the continents, you would expect the ranges of tropical forms to expand poleward, to go to cooler areas.
Yeah.
Didn't happen. Instead, they just disappeared. Okay. So the crocodile relatives, if it got inhospitably warm in the interior of tropical continents, would perhaps disappear there. But then at the edges, where it's too cold for them, they'd expand out. Didn't happen.
Yeah.
They just disappeared.
So we have a kind of severe cooling followed by a longer term effects of CO2. It's funny how
Pulses.
you,
There were pulses of these cold spells.
yes.
Once the first ones occurred, and I have to say first ones, we don't know if it was, 1 or 20. But the very first eruptions, once they occurred, and this collapse of the tropical ecosystems occurred, nothing goes extinct after that in the other pulses. The other pulses have no effect. And that's probably because the surviving floors were already not sensitive to the cold.
Yeah. It's funny how you mentioned a while ago, mentioned the French Revolution related to a volcano. The fact that it would lead to starvation because of the destruction of the ecosystem. Because I had
Yes.
someone else on the podcast who talked about how he lightly contributed Napoleon's downfall to a volcanic eruption as well, because it disrupted the ionosphere, which meant that there was a heavy downpour around the Battle of Waterloo, which contributed to his loss.
Contributed, yeah, yes, yeah. So there were a lot of things going on with the French Revolution, right? It wasn't like one thing, but certainly the combination of crop failures and mismanagement together was really bad. And it wasn't just in France, of course. This occurred all over the northern hemisphere. So there were problems like that. So, but then in France, it had a political outcome.
Yeah, sure. Well,
So
we've run over our 20 minutes. We're now at 45. So I think we should leave it there for the time being. And perhaps if you're more,
can I make one concluding kind of comment?
yes, please. Yeah.
So what I think we learn about this whole uh, overview of the end Triassic extinction is that basically we had dinosaurs all wrong. They weren't tropical organisms living in places that was warm all the time. Instead, they were already adapted from the very beginning to cold. And when the environmental changes occurred from the Central Atlantic magmatic province with these volcanic winters, they easily survived it. And their competitors in the tropics were completely wiped out, and they expanded over the world. And that's when we really get the beginning of what everyone's familiar with as the age of dinosaurs.
Life will out. Paul, thanks very much for coming on the podcast. I really appreciate it.
Sure. My pleasure. It's been lots of fun.
Thanks.